ladies and gentlemen, thank you for inviting me. You can see the authorship of this presentation. It's a little bit like the United Nations, but that's no bad thing for that. Contributors from the UK, from Iran, from Germany, and from the Netherlands. I'm going to have to say a few things by way of giving you a framework, and then I want to tell you about the new things that come on from there. You all will be aware that dealing with fine cohesive sediment in estuaries, particularly in ports, is a challenge. As soon as you touch this sediment with high pressure water devices of any kind, you tend to fluff it up and dilute it. And once you dilute it, you can't undilute it. So you end up with hoppers of dredgers that are full of what we call black water. And you can't increase the concentration by pumping, because you just pump more black water. And then you carry it out to seaward and dispose of it, and it spreads a long way. And we know from tracer tests that a lot of it comes back onto the shore and into the port. If you put it on shore, it needs a large area and it takes a long time to dewater. It's a really challenging material to deal with anyway, but I want to alert you to something new that we're understanding in Europe that is happening to our estuaries, and that also induces a challenge to us. So, by way of introduction, for centuries access to shallow muddy ports has been facilitated by dredging. The last 50 years as well has seen this sharp rise in ship size and draft to cater for these rises in the draft and size of ships. Ports and fairways have needed to be dredged deeper, and suddenly we've become aware of a severe problem which has manifested itself and leads to a lot of really intractable questions. I'm going to briefly show you what they are. But another challenge, as well as the black water and all this kind of thing, is can we undo the damage that we've already caused by our smart, clever, knowledgeable, high-tech way that we've been managing our estuaries in the past? And can we devise better, cheaper, more resilient means of managing muddy ports without dredging, while still admitting the deepest draft vessels? Well, this screen dump here, or slide, shows that I'm changing slides, and I don't intend to. Here we see two views of the estuary of the Loire in France, and it shows you a chart from 1887 versus 2003. And you can see that in the former times, this estuary was very wide. It had broad intertidal zone. It had many offshore islands and meandering and bifurcating channels, which caused the incoming flood tide to have to overcome a large amount of drag in order to carry the tide into the inner part of the estuary. However, as time has gone on, these estuarine systems have had their margins reclaimed, the islands have been taken away, and this and other big estuaries in Europe have been converted into single channel systems, such as this one. It's been over-deepened and over-deepened repeatedly, and even in some reaches, groins have been placed, perpendicular groins, to canalize even more the flow, all to accommodate deep draft ships. And I'm going to tell you in a minute what the consequences are. Just to show you that the Loire isn't unique, here's some information from the Ems estuary, and if I showed you the Elbe or the Scheldt or the Weser. We're now understanding that they are pretty similar too. So this is the small Ems estuary. You'll see Papenburg mentioned, Hebron mentioned, Lear might be mentioned, Emden will be mentioned, where we've done a lot of work, and just a little bit to seaward, but on the Netherlands side, the port of Del Soil. And the purpose really of showing you this slide is that you can see a graph here of concentration on the vertical axis versus distance from this point here in the estuary. And what it shows with the green, the blue, and the red lines is that because of over-deepening over a period of time, the turbidity maximum has become more intense and has migrated progressively up the estuary. So it gets to, on this graph, as high as 1 gram per litre. But if you look down here, it says what I've just told you, the evolution of the estuarine system, but mentions that concentrations actually reach 40 grams per litre. That's fluid mud. That's really fairly dense stuff. And this is the launch of a cruise liner. The Germans, in their infinite wisdom, insist on building cruise liners, really giant ones, at shipyard at Papenburg. And when they launch them, they only come down here once after launching. They have to take the high power transmission lines down and all sorts of things to get these big ships out. But the point of the slide really is to show you that it's this black water stuff, which is really difficult to deal with. So coming to what that discovery teaches us, and concentrating over here on this part of the slide, this is a diagram, I say, showing the feedback loop in deepened and canalized estuaries leading to very small tidal damping and hyper-concentrated mud conditions. So the picture itself, or the behavioral model, conceptual model, lays the blame. This is the enemy. We don't want it to be the enemy, do we? If ships get too big, then they require too much deepening and narrowing of the channel. And too much deepening leads to tidal amplification. And tidal amplification leads to an increase in tidal asymmetry. And that induces pumping of mud. And pumping of mud leads to drag reduction. And drag reduction causes more tidal amplification. And that goes round and round and round. And the first time I heard this, it's absolutely brilliant work. I thought I was an expert in estuaries, in muddy estuaries, until I heard this presentation. And it really rocked everybody in that lecture hall on their feet, because this loss of the multiple friction factors is called, by us, loss of resilience. And when we were all sitting there, the first time we ever heard that talk, all of us had our mouths open. We were so shocked to be exposed to that new information. And I think I was the first person to ask the speaker. I said to him, is there a tipping point when this sort of behavior begins? And he said, I don't know. So I said, well, how do you stop it? He said, I don't know. I said, do you know what the end point is? He said, I don't know. I said, how do you re-establish the resilience? What's the end point? He said, I don't know. Well, of course, in conceptual terms, we do know, because you've got to put it back the way it was, like I showed you 1887 from the Loire. But if somebody's built a great big city like the city of Rotterdam, in the meantime, you can't easily put it back the way it was. So this is a real cautionary tale about how clever Europeans, all of us, have managed coastal systems, and how are we going to get out of this one, guys? How are we going to get out of this one? So, Dr. Saltampur has said to you that in my career, began in 1965, looking at mud in ports for port authorities. But in 2008, we published this study, a PIANC study, in which we looked at all of the generic sediment management systems whereby we could maintain estuarine systems and ports without carrying away and deepening the system by dredging. So entrance flow optimization, it's only a part solution. Trickle auto flushing, I call it, but it is a total solution where it's best employed. We have 4 systems like that. One of them at that place, Lear. I showed you the port of Lear on that little map of Emden. Passive nautical depth. The pioneer port for that was Port of Rotterdam in 1974. Myself and one other British colleague and a Dutch colleague came up with a concept that we call nautical depth, but we now call it passive nautical depth. And finally, either two new systems or one with 2 parts. Active nautical depth. This is where we deliberately go out and create navigability where there wasn't any before. And to create that navigability, we need to manipulate the physical system, the chemical system, and the microbiological system. And that also, where you can make it work, is a total solution. And I call these anti-siltation technologies related to suspensions. And they're nothing whatsoever to do with dredging. So we have, 41 years experience with nautical depth in Rotterdam, and it's spread all around the world. We have 26 years of experience in Emden. We have 7 years experience with the same thing in Delfzijl, and we're just beginning with Husum in Germany. We're just beginning, we think, to understand properly the relationships between grain size and microbiological scope in anticipation of considering the application of these technologies more widely. And there's the vessel in operation that we use in Emden. You can see here the vessel is owned by Boskalis. It's a former trials vessel called the Meerval, and it's working in Emden entrance, and that's just a car carrier behind it. And if you look down into the hopper when it's working, you can see mud, which will be kind of pale grey coming up from the bottom, fluid mud. And you can get the impression, I think, from those swirls that it flows a little bit like, if you've ever seen the television, or if you've been there, to Hawaii, where volcanoes erupt and it's a very alkali lava and it flows very gently down the slopes. Well, this stuff also flows very gently from an inlet, which you can see is about here. There's the stuff coming in just about there. And then it flows to the outlet, and we put it down on the bottom again. And when it comes in, it's this pale grey colour, and when we put it back down, it's nice and pale brown and muddy, and it's the same stuff. So it's the opposite of water injection dredging. Water injection dredging uses high-pressure water jets to entrain bed deposits, which are then flushed away by the currents, if it works. But we use a very low engine speed, a low-power submerged dredge pump to gently raise the mud. The dredge pump destroys the developing interparticle bonds, fluidizing the deposits, and the uptake of air, as you're seeing happening here in the hopper, shifts the chemical climate in the mud back in the direction of the oxygenated state that we want it to be in, and reinvigorates the aerobic bacteria. Isn't nature wonderful? So, there you go, folks. You knew if you were patient, I'd get there in the end, didn't you? So that's the background, so you know what it is I'm talking about. So active nautical depth offers twin opportunities, and I'm now going to talk to you about some of our new work. It's like both sides of the same coin, really. In the first case, vigorous aerobic bacteria secrete copious amounts of EPS, slime you can call it. The purpose of the slime is to fill the pore spaces and prevent the fluid mud from dewatering. Note, we don't use any additives whatsoever. It's all nature. And what we create is permanent hindered settling mud. And by doing that, in its stable, engineered, creamy emulsion type stuff, it looks like non-drip paint. If you've ever decorated your home and used non-drip paint, that's what it looks like. But we need, because we create something which is stable, hindered settling becomes the permanent condition. We need minimal short-term manipulation, so that makes the whole process economic, but also the slippery suspension with all this slime allows ships to sail through the mud, you see, and it works very well. But the new other thing that we're learning to do is that not the EPS, well, I should say up there, the oxygen regenerate the bacteria, and the bacteria create the slime, and it's the slime that does all this work for the ships. But the other side of the coin is that the bacteria themselves have been found capable of destroying in situ the molecular structure of certain really pernicious organic contaminants, for example, TBT, which is something that is in many ports still around the world. So one thing that we've just been doing with these Iranian colleagues is we've been doing some tests in which we've compared Northwest European sediments from all these places to mud that we've had from Imam Khomeini port and from Bushehr. And just to compare them, you can see here that these Persian Gulf muds are low in organic content, but no different really from Emden, which is our prototype port, that the clay content, which is fairly low in Emden, is not much different from Imam Khomeini port, and the silt content, which is high in Emden, is comparable to the silt content in these Persian Gulf sediments. So, made us think, wow, maybe they're not so different after all. So these are some yield stress curves for these Persian Gulf sediments compared to Northwest European ones. Not quite the same. This is Emden, Rotterdam, Delfzijl, and Durgank Dock is in Antwerp. But here you see on this axis the yield point, and here the density. So you can see that there's a whole family of curves of the yield strength of these deposits, and the only thing different about these, well, I should say that these Persian Gulf sediments turned out to be quite weak. They failed at a yield point of about 3 to 6 pascals. But the only thing that's a bit different about them is that they seem to be, well, they are a bit more dense, and I put that down, unless anybody knows better, to the fact that there's these orthogenic carbonates in there. So it begins to look promising, and we're thinking of doing some more. But coming to my other subject, this is the natural degradation of TBT in an oxygenated environment in Emden muds. So this is a table. You can see that starting in October 1992, these are the number samples. This is the top of the mud, and this is the bottom of the mud. And you can see that at the top and the bottom of the mud, initially the concentration of TBT was quite high, and when it was monitored through time, it got lower and lower until it got virtually to background. And all this kind of squiggly stuff here is the mean concentration of TBT in micrograms. SN is the chemical symbol for tin, per kilogram of dried mud. And you are going to say to me, is that guy really going to say this is going to make a new industry out of a few chemical analyses? Well, no, not just that, but we know that similar things happen to mud, for example, at the port of Bremen, but the authorities land the sediment at Bremen and manipulate it on shore. But I've spoken to Iranian colleagues, and I'm not sure that you're so familiar with this, but we're getting familiar with it in Europe. Farm manure and human sewage can now be collected together, put in a tank, and if you have the right kind of bacteria, of course, the bacteria will generate methane. Methane will be used to turn a turbine, and a turbine can be used to create electricity, and you can create enough electricity by doing that to power a small village or a big village or a small town. So we actually have a name for it, of course, and we call it waste to energy, and it's really clever microbiology. So yes, we are thinking that there's industrial prospects of this, and we're calling it marine bioremediation. I should say that, unfortunately, but do not blame the port industry. Through no fault of its own, the port industry has a very poor record of dealing with contaminated sediment. Many port facilities around the world are silted up and abandoned because of the uneconomic cost of removing and disposing of their contaminated sediment. I could give you a talk about it, but I won't. Just a couple of examples. The port of New York, New Jersey is famous, infamous for having a really severe contaminated sediment problem. Nobody would have that sediment ashore. They were not allowed to put it offshore, but they really felt they had to carry out a capital dredging campaign to increase the capability of the port. And what they actually ended up doing was loading it into barges, towing the barges down the east coast of the United States, around the Florida Peninsula, into the Gulf of Mexico, up the Mississippi, unloading them and putting them onto rail cars and taking the rail cars to the Arizona desert. So New York can do its work, but the Arizona desert's got a pile of mud contaminated with some nasty contaminant. It doesn't solve the problem, it just relocates it somewhere else. Port of Falmouth in the UK had a TBT problem. Port of Falmouth is right on the far western tip of Cornwall, the bit that sticks out furthest into the Atlantic. And they couldn't get rid of their TBT contaminated sediment either, and they wanted to develop. So they ended up by loading theirs into rail cars and taking it to empty brick clay pits north of London. So they were able to do their work, but now we have clay pits in the northern part of London that are full of TBT, contaminated sediment. So our question arose in respect of these kind of problems, whether this accidental TBT destruction that I've shown you on that table in Emden could be converted into a viable engineering method. We already know, as well as what I've told you about waste to energy, that natural self-cleansing of contaminants occurs. So this is what we've begun doing this year. Academics in Liverpool were seeking to set up and run a new research facility under this title here. It's Liverpool John Moores University and our National Oceanographic Centre in the city. When I was a boy, I worked for them. They ran an internal competition to home in on a topic for that institute, and they very carefully appraised 4 prospects, one of which was my suggestion that I've just explained to you. But bear in mind, it was my suggestion, but not my scientific discovery. It's a scientific discovery of one of our German colleagues in this group. So what we've done is we've put together a proposal for a research grant application to the EU under the Blue Labs Innovative Solutions for Maritime Challenges, Water Framework Directive, all this kind of stuff. If you want to apply for EU money, you've got to walk the walk and you've got to talk the talk. That's the way it's got to work. And we're still just waiting for the outcome of that study, but we don't care really if the EU comes up with the money or not, because lots of people are offering to sponsor us anyway, because they think it's a good prospect. We're calling it marine bioremediation using active nautical depth, and the EU likes these acronyms, so it's our Mariana project. And we're thinking of setting up this laboratory, as I say, in Liverpool, and I won't start describing really the experiments we're thinking of doing, but it'll be directed by my German colleague, who's the guy who found out how to do it in the first place. So I'm nearly at the end. Here we are with a photograph of the things that do the work. The red things are the clay flakes here. The blue stuff is the bacteria, and this pale stuff is this EPS, this slime. And just to say a few words here, sediment and fluid mud particles are colonized by a broad spectrum of bacteria, most of them embedded in microbial biofilms that offer the optimal microclimates for even the most complex degradation process. And you see, I also use the word biofilm there. And the reason why I use the word biofilm twice is that my German colleague assures us that most of this chemical activity or biological activity takes place in biofilms that cover contaminated sediment particles. So, by way of conclusion, this is my last slide up there. I've shown that excessive deepening of muddy estuaries and port approaches can be highly damaging, damage that we can't easily rectify. On the other hand, we could let them fill with mud and then sail through the mud. So that's one way, or one contribution towards this problem of how do we restore our degraded estuaries. Our PIANC MHS report, I showed you that we have these generic sediment management systems that we're hoping to deploy through this new contracting company that we've set up in Holland for doing this work. And we say these are anti-siltation technologies related to suspensions, and they have nothing whatsoever to do with digging up and carrying away bed material. And these are technologies arising from science, not from classical engineering. But I do say, and I tried to explain it to you, that really these are two sides of the same coin, the biology operating in different ways. So can nautical depth technologies be applied more generally? The analyses of these Persian Gulf materials encourage us to think that they might. They would be cheaper, better, more environmentally resilient and sustainable if they could be. So the economic success of many muddy ports is constrained by the incursion of mud, which is too contaminated to be dealt with by traditional methods. And now we've begun with this Mariana initiative, and the initial focus will be on TBT. And I laugh because of the next line. It could develop into a new industry, but in reality, look at this. There's not one chemical in the subaqueous environment. There are 22,000 named anthropogenic contaminants in the subaqueous environment. Well, you could say you've got plenty to go at. We don't in any way think that we're going to solve all of those problems, but I know certain metals that are susceptible and certain organic compounds that are susceptible, as well as TBT, and so we've got a platform to start. We're never going to address 22,000, and it really requires an international scale of effort, which may be focused on this Marianas initiative. So we have some current indications of acceptance. We've got 4 jobs at the moment for this new contracting company, and some nice things have happened too this year that I'll just say to you finally. One of them is that I've always had problems dealing with our environmental agencies. I write to them and they ignore me. Who am I? Why do I need to reply to this geezer? They just don't need to. So I did write to Piank headquarters about it, and headquarters staff have said, if you need to deal with them again, you can use us as an umbrella. So that's good for us. It's wonderful to not be on my own after 40 years of being on my own. We have a big Dutch company has said, oh, we would like to work with you. So we've said, oh, thanks. That was great. And finally, when we set out the program for this Mariana initiative, it came up with a cost of 800,000 euros. But the ceiling for an application under this Blue Labs initiative is 500,000 euros. So that wasn't very viable. But a day and a half later, I got a phone call from Liverpool, and they said, we've decided to scrub around all of our staff time and throw out all of our capital items of equipment, and we'll use it with our own equipment that we've got already. So that was all these 3 things are fabulous shows of support that I've never been accustomed to before. You know what? When I started in 1965, trying to help ports and to understand muddy systems in a practical way, if somebody had said to me, bacteria are important to ships and fine sediment, I would have definitely said they're crazy. But here I am, 50 years later, and I'm telling you, in the way that I've described, that bacteria are important to ships. For world trade, we need successful ports, but here in muddy areas we already have efficient ships and landside management. Nobody thinks of having an inefficient container yard. We've been let down in the past by the backward nature of our waterside management, and in the 2 ways that I've tried to show you briefly, we can do and must do much better. Ladies and gentlemen, thank you for your time.